Problem number 8. Calculate the drive shaft power and flight size for a 18.3 meters flight conveyor to transport 36 tons coal per hour at 30.5 meters per minute. Inclination 30 degrees, effective flight area 30% of surface area, allow 22.3 kg per meter for stand weight. Standard flight sizes are 30.4 centimeters, 38.1 centimeters, 45.7 centimeters, 61 centimeters wide, and 10.2 centimeters, 15.2 centimeters, 20.3 centimeters, and 25.4 centimeters high. So for the solution for problem number 8, so S is equals to 30.5 meters per minute. So from table 12.2 of Morse, flight conveyor is tons per hour is equal to 48.055 AS. So 36. So plugging in our values, so 36 is equal to 48.055 A times 30.5, which is our S. So deriving this formula, so A now is equal to 36 divided by 48.055 times 30.5, which will give us a result of 0.024562 meters squared. So for flight area is equal to A divided by 0.3, which is equal to 0.08187 meters squared, or it is also equal to 818.7 centimeters squared. So we have to select this 45.7 centimeters by 20.3 centimeters. Therefore, area now is equal to 927.71 centimeters squared. So for drive shaft power, so 0.00198 WTLS plus 0.00256 TL, where W sub T is equal to 23.3 kilograms per meter, and L is equal to 18.3 meters, S is equal to 30.5 meters per minute, and T is equals to 36 tons per hour. So substituting these values in this formula, we have 0.00198 times 22.3, which is our W sub T, and our L 18.3 meters. Next is our S is 30.5 plus 0.002567 times 36 times 18.3, which will give us a result of 4.11567 HP. So for inclined conveyor, add TH over 273.7 HP. So H is equal to S sine 30, which is S is 30.5 sine 30, which will give us a result of 15.25 meters per minute. So 36 times 15.25, which is our H, divided by our 273.7, which is stated here, will have a result of 2.0058 HP. So lastly, for our drive shaft power, is equal to 4.1567 plus 2.0058, which is equal to 6.1628 HP. So that's all for number 8. Problem number 12. On number 5, residual oil weighted 250 SSU at 37.8 degrees Celsius is to be burned in a centrifugal type atomizer. Will it require to be preheated if its tank temperature is 15.6 degrees Celsius? If the same oil were to be burned in a pressure atomizing burner, how many watts electrical input would be required for the preheater when flow is 3.79 liters per minute. Assume specific gravity of 0.93, specific heat 0.55 kilocalories per kilogram per degrees Celsius. So number 12. So from figure 12-21, 250 SSU, 37.8 degrees Celsius centrifugal type atomizer, desired temperature is equal to 17 degrees Celsius. Therefore, for our required is our Q. So Q now is equals to mass times C sub P times delta T. So Q now is equal to 3.79 times 0.93 times 0.55 minus our delta T, which is 17 minus 15.6, which will give us a result of 2.714 kilocalories per minute. So converting it to watts, so 2.714 kilocalories per minute times 4.187 kilojoules per kilocalories times 1 minute over 60 seconds times 1000 watts divided by 1 kilowatts. So all units will be cancelled except for the watts. So Q now is equal to 190 watts. Problem number 13. Find the steam consumed per hour to preheat heavy oil for burning in a steam atomizer per 3.79 liters per minute flow. Assume specific gravity of 0.97, steam at 14.1 kilogram per cubic centimeter, saturated, oil in tank heated to minimum required temperature for pumping, viscosimeter, test on oil SSU 1150 at 43.3 degrees Celsius. So let's move on to number 13. So figure 12-21 by Morse, preheating needs in fuel oil system. So for SSU 1150, 43.3 degrees Celsius steam atomizer B, from figure 12-21, tank oil temperature required is equal to 75 degrees Fahrenheit. So converting it to Celsius, which is equal to 23.9 Celsius. So projection downward to the right of the line B shows that the oil should be heated to 141 degrees Fahrenheit or converted to Celsius, which is 60.6 degrees Celsius before atomization. So heat balance. So M sub S is equals M sub S times H sub Fg is equal to M sub 0 times C sub PO, M sub O times C sub PO times delta T or T sub O2 and T sub O1. So M sub O now by deriving this formula, M sub O now is equal to 3.79 liters per minute times 0.97 times 1 kilogram per liters divided by 60 minutes per hour. So M sub O now is equal to 220.578 kilogram per hour. So at 14.1 kilograms per centimeter squared of G is saturated. So therefore, H sub Fg now is equal to 1,947.2 kilojoules per kilogram. So for specific heat of oil, assume a 0.45 BTU per pound feet is equal to 1.884 kilojoules per kilogram K is equal to C sub PO. So from the formula, so substituting our values, so M sub S times 1947.2 is equal to 220.578 times 1.884 times the delta T or our 60.6 minus 23.9. So m sub s now is equal to 7.8325 kilogram per hour. So that's all.